Okay, so the first problem from JAM 2021. Let W be a subspace of the vector space R3 over the field R, which is spanned by these two vectors 0, -1, 2 and 2, -1, 0. Which one of the following vectors lies in W? Four options are given. The first one is 1, 1, 1, second one is -1, 1, 1, third is 1, -1, 1, and the fourth is 1, 1, -1. Now note carefully, when you are solving this kind of sum, always remember one thing in mind, that any linear combination of these two vectors lies in W. Say for example, when you are simply adding it, that will be inside W. So what will be happening when you are simply adding them? When you are adding them component wise, that is giving you 0 plus 2, -1 -1, 2 plus 0. That means this is giving you the vector 2 -2, 2. Now note carefully, this is a linear combination, so that is inside W. Now if you multiply anything with this vector, that will be inside W as well. Now is there any scalar that when getting multiplied with this one reaching out to any one of the options? The answer is yes. If you multiply that with half, that will giving you 1 -1, 1, which is option C. So C is inside W. So C is the correct option. Let us move to our next sum from JAM 2022, question number 6. Let W be a subspace of the vector space R3. Then which of the following set of vectors forms a basis of W? Four options are given, but note carefully, this question is incomplete. Nothing else is mentioned about the subspace W. So actually this question was incomplete and marks was awarded to all the candidates who attempted it. But still, we'll discuss the sum from a different perspective. We'll discuss a very powerful trick that will help you to solve this kind of sum very easily. So let us move to that. Suppose S is a subset of R3. So when can you say that this S is linearly independent or not? Or in other words, vectors in S is linearly independent or not, just by having a look or minimum calculation involved. So here we are just listing out a very basic points that if you keep in mind will help you to solve this kind of sum extremely fast. So let us start. Suppose your set is containing 0, 0, 0, that means the 0 vector. So whenever your set is containing the 0 vector, it will always be linearly dependent. You do not require to take a look to anywhere. Next, suppose your set is containing exactly one vector and that is non-zero. Then that set will always be linearly independent. Next, if your set is containing exactly two vectors and they are non-zero, then that set will be linearly independent if those two vectors are not scalar multiple to each other. For example, if you are considering the vectors 1, 1, 1 and 1, 2, 3. Now note carefully, you won't be able to get any scalar C which when getting multiplied with 1, 1, 1 will produce 1, 2, 3. So these two vectors 1, 1, 1 and 1, 2, 3 are not scalar multiple to each other. In this case, you will be able to say that those two vectors are linearly independent. Otherwise, you will be able to say those two vectors are linearly dependent. Next, let us come to the case of three non-zero vectors. Now, suppose S is a set containing three non-zero vectors A, B, C, X, Y, Z and P, Q, R. Now, this set of vectors will be linearly independent if this particular determinant is giving you non-zero value. And finally, if your set has more than three vectors, then this set will always be linearly dependent. Now let us get back to our sum. Now definitely we know nothing about W and therefore it is not possible to answer this question completely. But even without knowing anything about W, it will be possible for us to discuss at least two options from these four options just by using our very powerful tricks that we have just learned. Now first of all, note carefully, here you have been asked to say which of the following set of vectors forms a basis of W. Now what they mean by a basis? A basis is a spanning set which is linearly independent. So let us check which of the following four set of vectors can be linearly independent here. Note carefully, when you are considering option A, you have been given just two vectors, and two vectors will be linearly independent if they are not scalar multiple of each other. Note carefully, here the vectors you have been given is 1 to 1 and 1 minus to 5 in R3, and definitely they are not scalar multiple. So definitely by the trick that we have learned, we can say here that this set of vectors is linearly independent. Let us move to the next one, option number B, where we have been given four vectors. Now they are asking, can it form a basis? So we'll boils down to the question, is it a linearly independent set? The answer is no. We have just learned that if there are more than three vectors in R3, they cannot ever be linearly independent. So definitely B cannot be basis. Let us come to C. Now C has three vectors. Are there those three vectors linearly independent? So how do you check whether three vectors are linearly independent or not? Will form corresponding determinant. So the determinant having first vector in the first row, second vector in the second row, and third vector in the third row. If the value is 0, then these three vectors will be dependent. If it is non-zero, then those three vectors will be independent. Now let us calculate the value of the determinant. If you expand it about the first row, you will be getting the first term as 2 plus 3, the second term as minus of 1 minus 6, and the third term as minus 1 minus 4. So basically you are getting 5 plus 5 minus 5. If we cancel out 5 and minus 5, we'll be getting 5, which is non-zero. So definitely by our trick that we have learned, we can say that these three vectors are linearly independent. Now let us come to D. Can the vectors given in D be linearly independent? Once again, we'll do the same thing. We'll form the determinant where the first row will be the first vector 1 minus 2 1, second row will be 2 1 minus 1, third row will be 7 minus 4 1. Now if we expand it again about the first row, we'll be getting the first term as 1 minus 4, second term as twice 2 plus 7, and third term as minus 8 minus 7. So that will be equal to minus 3 plus 18 minus 15. Now this time this is giving the value 0, and whenever this is 0, the three vectors cannot be linearly independent. So definitely once again these three vectors cannot form a basis. So already we have removed option B and option D from our cut. So the only possible answers for us are option A and option C. So that is the power of the tricks that we have just discussed. Next sum from JAM 2021, question number 10. Let those two denote the standard norm and standard inner product in Rn respectively. If uv belongs to R3 such that norm of u is equal to norm of v is equal to 2 and the angle between uv is pi by 3, then which of the following four options is correct? First of all, we'll note one thing, that whenever we are talking about standard norm in Rn, it is nothing but the length. And whenever you are talking about the standard inner product in Rn, it is nothing but the dot product. So whenever you are trying to calculate norm of u, inner product of u and v, it is nothing but the basic dot product of u and v in R3. How do you calculate this? Inner product of u and v, that means the dot product of u and v, is just length of u times length of v times cos of the angle between them. So cos pi by 3. So what is length of u? It is nothing but the norm of u, which is equal to 2. Similarly, norm of v is equal to 2 as well, and cos pi by 3 is half. So that means you are getting the value of dot product of u and v to be 2, is not is equal to 2 root 3. So B is wrong. Let us move to option A, where we are supposed to calculate norm of u minus v. So what is the formula for norm of u minus v? Norm of u minus v is equal to under root inner product of u minus v with itself. So if you expand this inside the square root, you will be having u inner product of u with itself minus inner product of u with v minus inner product of v with u plus inner product of v with itself. Now note carefully, those two terms are equal, and therefore we can write this as under root u minus 2 inner product of u with v plus inner product of v with itself. Now note carefully that inner product of u with itself is nothing but norm of u square, and this is nothing but norm of v square. So in the next line we will be writing under root norm of u square minus 2 inner product of u with v plus norm of v square. Now let us put the value. What is norm of u square? We have seen that norm of u is 2, so norm of u square is 4. We have calculated inner product of u with v is 2, so the second term will be minus 4, and norm of v square is 4. So we can cancel them out, so this is equal to 2. So we have obtained that norm of u minus v is 2. It is neither 2 root 2 nor 2 root 3. So we can cancel out A and C. So finally let us check the value of norm of u plus v. So norm of u plus v is equal to, using the similar formula, we can write it is equal to under root inner product of u plus v with itself. So which is, when expanded, will give you plus here, and that will become plus plus plus, so that will be under root 12, which is 2 root 3. Therefore D is the correct option.